On the night of 24 July 1943, at a radar post near Hamburg known as Himmelbett Eisbär, German operators encountered a phenomenon that seemed to defy everything they understood about radio detection. Oberwriter Klaus Hartmann, monitoring the Würzburg radar console, stared at the cathode ray display in disbelief. Instead of the usual distinct signals representing individual aircraft, the screen had filled with a dense cluster of luminous echoes. The returns multiplied until they appeared as an enormous, continuous formation, far more contacts than any realistic bomber force could produce. Hartmann noted his observations in the station log with visible uncertainty. Either an unprecedented Allied air assault was underway, or British forces had introduced an entirely new tactic. The radar indicated numbers of aircraft exceeding the total strength of the Royal Air Force. His technical training suggested a malfunction. His intuition suggested something far more troubling, an unfamiliar method of warfare. Across the German air defense network, confusion spread rapidly. Fighter control centers directed night fighters toward targets that vanished as pilots approached. Anti-aircraft units opened fire on formations that did not exist. Searchlights swept the sky in erratic patterns, unable to lock onto real aircraft. From the North Sea to the Ruhr, radar operators were overwhelmed by a flood of deceptive signals that rendered their guidance systems ineffective. That evening marked the opening phase of what would become the most extensive electronic warfare effort of the war. Allied jamming and countermeasure technologies began systematically degrading German radar capabilities. The disruption would prove as damaging as conventional bombing campaigns and would compel Germany to redirect thousands of specialists in radar and electronics away from other weapons programs in a desperate attempt to develop countermeasures. Germany had previously relied on a strong sense of technological confidence. Since 1939, the Luftwaffe had constructed an air defense network widely regarded as the most advanced of its time. Engineers at companies such as Telefunken had produced highly capable radio detection systems. Early warning Freya radars could identify incoming bomber streams at distances beyond 120 kilometers. Large Würzburg gun-laying radars provided precise tracking of individual aircraft, allowing controllers to guide night fighters close enough for visual interception or to direct anti-aircraft guns with accuracy. These systems formed part of the Kammhuber line, named after General Joseph Kammhuber, who oversaw Germany's night fighter operations. The defensive belt consisted of overlapping radar sectors stretching across the approaches to German territory. Each sector integrated ground-based radar with a single night fighter equipped with its own onboard Liechtenstein radar set. Together, these elements transformed night combat from blind searching into controlled interception, giving German crews a significant advantage for several years. Operators and pilots trained within this system developed strong faith in its effectiveness. Many believed German electronics and radar engineering were unmatched. Letters written by radar personnel in late 1943, later found in military archives, reflect that confidence. For years, they had tracked British bombers reliably and guided interceptors with precision. British reliance on darkness offered little protection against a network that could detect and follow aircraft almost as if they were visible in daylight. That certainty began to unravel during the July 1943 raids, when the familiar clarity of radar screens dissolved into chaos. Technically, the Würzburg radar represented a peak of German engineering. Operating on wavelengths around 53 centimeters and frequencies near 560 MHz, it could measure range with an accuracy of roughly 25 meters and determine direction to within a fraction of a degree. Yet even this advanced equipment proved vulnerable once the Allies introduced coordinated electronic countermeasures. The events of that July night signaled the start of an invisible contest fought through radio waves and electronic deception. One in which Germany found itself increasingly at a disadvantage. A large parabolic antenna, almost 8 meters across, turned on finely engineered bearings and followed aerial targets through an automated servo mechanism that represented the forefront of wartime technology. Factories throughout Germany produced these radar systems in large numbers. Each installation demanded more than 3,000 hours of skilled assembly and calibration before it could be deployed. by the middle of 1943, German radar stations formed a continuous defensive network stretching from Norway down to the French coastline. This electronic barrier had become a serious hazard for Allied bomber crews. Losses within RAF Bomber Command rose steadily during 1942 and into early 1943 as German night fighter units refined their coordination with ground-based radar. In March 1943, operations against Berlin cost Bomber Command 5.2% of the aircraft sent. Attacks in June against the Ruhr resulted in 4.7% losses. Such figures could not be sustained over time and threatened the viability of the entire strategic bombing effort. Air Chief Marshal Arthur Harris concluded grimly that at those rates Britain would exhaust trained aircrews before Germany ran out of cities to defend. American forces flying daylight missions encountered comparable dangers. B-17 and B-24 formations of the U.S. 8th Air Force passed through layers of anti-aircraft fire guided by radar with mechanical accuracy. German Würzburg radar tracked bomber formations and supplied data to analog predictor systems that calculated where shells should be fired to intersect with the aircraft. On deep missions into German territory, American losses frequently climbed above 10%. The Schweinfurt mission in August 1943 proved especially costly. 60 bombers failed to return out of 376 dispatched, a loss of roughly 16%. This level of attrition nearly undermined the American strategic bombing approach. Meanwhile, British and American researchers had been quietly developing countermeasures that would soon transform the air war. Secret work at Britain's telecommunications research establishment in Malvern and at Harvard's Radio Research Laboratory in the United States focused on methods to disrupt enemy radar. Beginning in 1942, scientists in both countries explored ways to confuse radar detection systems. Their efforts eventually produced techniques capable of overwhelming German radar networks. One of the most effective ideas came from Joan Curran, a physicist working with the British Radar Countermeasures team. She experimented with narrow strips of metallic foil and discovered that pieces cut to half the wavelength of German radar signals reflected pulses extremely well. Although each strip cost almost nothing to manufacture, it produced a radar echo comparable to that of a large aircraft. When thousands of these strips were released in the air, they formed a cloud of false signals that cluttered radar screens and concealed real targets. The concept was straightforward, yet its use was postponed for over a year because both sides had independently developed similar technology. German researchers had created their own version, known as Düppel, named after a Berlin suburb where tests were conducted. Each side feared that using the technique first would invite immediate retaliation. Frederick Lindemann, Winston Churchill's chief scientific advisor, strongly opposed deploying the British version called Window during early discussions. He warned that once introduced, the Germans would quickly copy the method and use it against Britain's own air defenses in any renewed bombing campaign. Memories of the Blitz influenced both fighter command and anti-aircraft planners, and for 13 months the technology remained unused. By July 1943, however, circumstances had changed. Most German bomber units had been reassigned to the Eastern Front, and attacks on Britain had become infrequent. Intelligence also suggested that Germany had not adopted new radar frequencies resistant to this type of interference. British leaders therefore approved operational use. The upcoming bombing of Hamburg Operation Gomorrah would introduce the countermeasure and mark a turning point in electronic warfare. Production began rapidly. British factories, including facilities connected to the Ministry of Aircraft Production, started turning out vast quantities of the foil strips. Each packet contained about 2,200 pieces of aluminum-coated paper roughly 27 centimeters long and 2 centimeters wide. At first, many of the workers, often women recruited for wartime industry, cut and bundled the strips by hand. As demand surged, more automated processes were introduced. By late July 1943, output exceeded 200 million strips per week, enough to supply every bomber involved in operations over Germany. Deployment was carefully organized. On July 23, 24 Lancaster crews received detailed instructions about the new equipment. Flight Lieutenant Harold Martin, who had previously taken part in the Dambusters raid, noted in his log that crews were instructed to release bundles of what resembled festive tinsel through the aircraft's flare chute at 1-minute intervals, using a stopwatch to maintain timing. Intelligence officers assured them that this simple procedure would disrupt German radar completely. Many airmen remained skeptical that small pieces of foil could neutralize an entire air defense network, but the results would soon become clear. The evening of July 24, 1943, began like many large bomber operations. Airfields across eastern England prepared 791 aircraft for a major assault on Hamburg. Lancaster, Halifax, Stirling, and Wellington bombers were loaded with combinations of high explosive and incendiary bombs designed to devastate the city. Explosives would tear away roofs and shatter windows, while hundreds of thousands of incendiary devices would ignite exposed structures and fuel massive fires. In addition to this destructive payload, each aircraft carried the newly prepared bundles of metallic strips, an innovation that would soon change the balance between radar defenses and the bombers they sought to stop. Bundles of metallic window strips packed in crates and ready for release had been loaded aboard British bombers and spaced for deployment roughly every 60 miles along the route toward Hamburg. Each aircraft carried enough material to generate a nearly unbroken curtain of deceptive radar reflections during the most dangerous phase of the mission, the final hour over German territory. Across northern Germany, radar crews began their night shift, expecting routine operations. At one installation, Oberleutnant Hartmann completed his checks with methodical care. The Würzburg radar set, operating under its assigned call sign, responded perfectly during calibration. Its screen displayed nothing unusual beyond the familiar clutter of ground echoes. Communications with Fighter Command at Stade were clear. Everything appeared set for another standard effort to guide night fighters toward incoming RAF bombers. The first hint of activity arrived around 22:30, when long-range Freya radar arrays detected aircraft forming up over eastern England. This pattern matched previous British tactics and did not initially raise alarm. At divisional headquarters, plotting officers traced the developing formation and calculated possible objectives based on headings. The bomber stream seemed likely to head toward the Ruhr industrial region or possibly Hamburg. Night fighter units across bases stretching from the Netherlands to Denmark were placed on standby for potential scramble orders. At midnight, as the bomber stream crossed the German coastline near Cuxhaven, the situation changed dramatically. Radar operators throughout the network saw their displays suddenly flood with signals. Instead of the usual trackable echoes from individual aircraft, screens filled with dense, overlapping returns that made identification impossible. What had been a manageable number of targets moments earlier now resembled vast formations spread across wide sectors. At Hartmann's station, the display that had shown a few distinct bomber groups now suggested hundreds of aircraft scattered across a front tens of kilometers wide. Fighter control rooms descended into confusion. Controllers attempting to vector night fighters found their instructions useless within minutes. Reports poured in. Radar indicated targets everywhere, yet precise positions could not be determined. With entire sectors showing continuous returns, directing interceptors towards specific bombers became impossible. Searchlight units, which depended on radar guidance, swept the sky without success. Every direction seemed to contain targets according to their instruments, but visual confirmation revealed only darkness. Anti-aircraft batteries faced the same paralysis. Their fire control systems required accurate range and bearing data from radar. Instead, they received contradictory information suggesting aircraft at all altitudes and bearings at once. Some gunners fired blindly into areas of apparent activity. Others held fire, realizing that random shooting wasted ammunition and exposed their positions. Night fighter crews experienced similar disorientation. Pilots flying Bf 110 seconds and Ju 88 seconds relied on onboard Liechtenstein radar to locate bombers in darkness. That equipment now displayed the same confusing mass of echoes. Major Heinz Wolfgang Schnaufer, already credited with numerous victories, later described the problem in his report. Signals appeared wherever he pointed his antenna, yet vanished or multiplied when he attempted to close in. Distinguishing genuine targets from interference proved impossible. Visual searching offered little help because the bomber stream was dispersed and difficult to spot. German fighters, deprived of their radar advantage, flew largely without direction. Meanwhile, 791 RAF bombers advanced toward Hamburg with minimal interference. Crews tasked with releasing the foil strips carried out their instructions and soon realized that German defenses were far less effective than expected. Only a dozen aircraft were lost that night, roughly 1.5% of the force, compared with recent missions that had seen losses around 5%. One British flight lieutenant noted that searchlights below moved aimlessly and anti-aircraft fire lacked accuracy. No night fighter successfully attacked his formation. The attack itself benefited from new technology. Pathfinder aircraft used H-2S ground mapping radar, operating at centimetric wavelengths to obtain clear images of Hamburg's coastline and waterways. They dropped marker flares accurately over designated aiming points, allowing following waves to release their bomb loads with unusual precision. High-explosive bombs damaged structures across targeted districts, and incendiaries ignited fires that soon merged into a massive blaze visible from hundreds of kilometers away. Later reports from Hamburg's fire services counted thousands of separate fires, overwhelming any attempt at control. As dawn approached and the RAF returned to England, German radar screens gradually cleared. The false echoes disappeared and equipment resumed normal operation, tracking departing bombers with customary accuracy, yet the psychological impact remained. For radar operators like Hartmann and for commanders across the air defense network, the night of July 24-25 marked a turning point. Proof that a simple technological countermeasure had temporarily crippled an entire defensive system. In the station records, Hartmann noted that German defenses had effectively been blinded by an unknown method. Whatever the British had used, it overwhelmed radar systems in a way German crews neither understood nor could resist. If repeated, he warned, the entire air defense network would be rendered ineffective overnight. His conclusion was stark. A system that had seemed advanced had suddenly become useless. The shock at Luftwaffe headquarters was immediate. General Joseph Kammhuber gathered radar engineers and fighter commanders for an emergency review. Their central question was how British aircraft had managed to neutralize German radar so completely. Early explanations focused on new jamming devices or perhaps a breakthrough in radar-absorbing materials. The reality turned out to be far simpler and far more damaging. As German personnel moved through the wreckage of Hamburg, they found the answer scattered across the city. Streets, rooftops, trees, and canals were covered with countless thin strips of metallic foil. Samples brought to Dr. Hans Pendel, the Reich's authority on high-frequency research, confirmed their worst suspicions. The British had deployed a radar confusion method essentially identical to one German scientists themselves had designed but never used, fearing retaliation. Now that hesitation had backfired. The consequences were severe. German planners had assumed British radar lagged far behind their own, so they had not prioritized defenses against this type of interference. With the tactic now exposed, every radar station in the German network was vulnerable to a cheap and easily deployed countermeasure. Efforts to find a rapid fix began at once, but the obstacles were overwhelming. Kammhuber later explained to Allied interrogators that the timing of the British deployment was devastatingly effective. If it had come 6 months earlier, German industry might have retooled to produce radar operating on different frequencies less susceptible to the interference. By mid-1943, however, production lines were fully committed. Electronics factories were already stretched thin by demands from V2 development, airborne radar programs, and other urgent projects. There was no capacity to redesign and mass-produce new systems in time. In the absence of a technical solution, German commanders resorted to a crude tactical workaround. Colonel Hajo Hermann proposed using single-seat day fighters as improvised night interceptors in an approach known as wild sow, wild boar. Pilots would be guided to general areas indicated by concentrations of metallic foil and then rely on visual contact spotting bombers against searchlights or fires below. The method achieved occasional successes but came at heavy cost. Many day fighter pilots lacked night flying training and proper instruments, leading to accidents and friendly fire incidents. The tactic underscored how quickly Germany's technological edge had evaporated. Meanwhile, the United States moved quickly to expand its own electronic warfare efforts after observing British success. American researchers at Harvard's Radio Research Laboratory, working closely with British teams in Melbourne, focused on active jamming systems that would directly interfere with German radar rather than merely producing false echoes. Their most effective device, known as Carpet, targeted Würzburg radars used to aim anti-aircraft guns. Unlike passive foil, Carpet transmitted radio frequency noise straight into German receivers. The AAPT-2 version installed in heavy bombers combined a receiver to detect German radar signals with a transmitter that immediately jammed them on the same frequency. For German operators, the effect was dramatic. Radar screens that once showed precise aircraft positions dissolved into chaotic static, making tracking impossible. Technical Sergeant Robert Chen, serving with the 384th Bomb Group, described the system's impact in a late 1943 report. While flying over enemy territory, he would monitor known radar frequencies with a search receiver. When a Würzburg signal appeared, he tuned a jammer to match and activated it. Almost instantly, anti-aircraft fire that had been accurate would become erratic, bursting at incorrect altitudes or drifting off target. Precision turned into guesswork. By the end of 1943, the combined use of metallic foil and active jamming had reduced German anti-aircraft effectiveness by roughly 3/4. Statistical reviews by the US 8th Air Force showed sharp declines in bomber losses on missions using these countermeasures. Crews reported that flak-related losses and severe damage rates dropped dramatically when both methods were employed together. The improvement translated into hundreds of aircraft saved and thousands of aircrew surviving missions that might otherwise have been fatal. German research teams responded with increasing urgency, attempting to devise new defenses against the growing sophistication of Allied electronic warfare. Laboratories across the country worked feverishly to counter the countermeasures, but the technological advantage had already shifted. Germany introduced a countermeasure project known as Laus, named after the German term for louse, to exploit a physical limitation in Allied chaff. Strips of metallic foil released by bombers drifted downward far more slowly than the aircraft themselves. German engineers theorized that radar filters could separate these slow-moving reflections from the rapid signatures of real aircraft, allowing operators to ignore the chaff and focus on genuine targets. At the same time, German designers began prioritizing radars capable of rapidly shifting frequencies. If a radar could change its operating band quickly enough, Allied jamming equipment would struggle to keep pace. One major step in this direction was the introduction of the few G220 Liechtenstein SN2 airborne radar in late 1943. Unlike earlier systems, it worked in a much lower frequency range, around 90 MHz, well outside the band for which Allied window chaff had been cut. The SN2 also used a distinctive forward-facing antenna array nicknamed Hirschquoe, stag's antlers, made up of large dipole elements projecting from the aircraft nose. Operating at lower frequencies enabled the radar to detect targets even in dense chaff clouds that had blinded previous sets. For a time, German night fighters regained effectiveness. Ace pilot Major Heinz Wolfgang Schnaufer, later credited with 121 nighttime victories, reported that the new system restored his ability to identify real bomber returns and maneuver into attack positions. This advantage did not last. Allied intelligence efforts were persistent and highly effective. In May 1943, a German crew led by Oberleutnant Herbert Schmidt defected to Scotland in a Ju-88 night fighter carrying early Liechtenstein BC radar. The aircraft landed largely intact, giving British engineers complete access to German airborne radar technology. Countermeasures followed quickly. The Serrate system, developed by Britain's Telecommunications Research Establishment, TRE, was a passive receiver that could detect Liechtenstein transmissions and guide RAF Mosquito night fighters toward German aircraft. German interceptors whose radars revealed their positions now found themselves targeted by aircraft using their own emissions as homing signals. An even more damaging intelligence windfall occurred in July 1944. A Ju-88G-1 night fighter equipped with the newer Fu-G220 SN2 radar and Fu-G227 Flensburg detector mistakenly landed at RAF Woodbridge in England after its crew misread navigation beacons. The plane and its electronic equipment were captured intact. British scientists quickly analyzed every aspect of the latest German radar and detection systems. New jammers were designed specifically to counter the SN2, with full knowledge of its frequencies, pulse patterns, and antenna characteristics. Among these was the Piper jammer, rapidly developed after the Woodbridge incident, installed on specialized electronic warfare aircraft within RAF Bomber Command's number use of the Section 100 group. Piper generated a protective zone of interference behind the host aircraft. Bomber formations flying within this zone were far less vulnerable to German night fighter interception. Losses that had been severe during the winter 1943-44 Berlin campaign fell sharply once these systems were widely deployed. German personnel increasingly recognized that they were losing the technological contest. By late 1944, radar operators reported that each new system or frequency was quickly detected and jammed. Allied aircraft used German emissions as navigational beacons, while jamming rendered German gun-laying and interception radars unreliable. Many crews were forced to rely on visual detection, as in earlier conflicts, while the Allies operated with growing control over the electromagnetic spectrum. The cumulative impact of Allied electronic warfare placed enormous strain on German resources. By 1944, roughly 7,000 specialists, engineers, and scientists who might have supported other weapons programs had been reassigned to radar and countermeasure development. This represented a large share of Germany's high-frequency radio expertise. Production facilities continually retooled to build revised radar sets or new frequency variants, many of which became obsolete almost as soon as they entered service. Strategically, the consequences extended beyond the radar battle itself. Germany expanded fighter and anti-aircraft defenses to compensate for degraded radar effectiveness. By August 1943, nearly half of German fighter aircraft were assigned to home defense rather than supporting ground operations. Anti-aircraft gun deployments also grew substantially, requiring additional personnel and resources. Industrial output increasingly shifted toward protecting German airspace from bomber streams that radar systems could no longer track reliably. This redistribution of effort weakened support for ground forces on multiple fronts and represented one of the most significant indirect outcomes of Allied electronic warfare during the war. The strain on German resources was not limited to equipment. Manpower shortages became just as damaging. Anti-aircraft defenses inside Germany eventually consumed roughly a quarter of all munitions being manufactured. Maintaining those batteries required so many personnel that nearly 1 million men were diverted from other combat roles. Soldiers who might have reinforced the Eastern Front or helped defend the French coast instead stood beside radar-directed guns whose effectiveness had been sharply reduced by Allied electronic interference. The human effect of this technological struggle was severe. Radar technicians and fighter pilots increasingly felt they were operating at a disadvantage they could not overcome. One operator, Klaus Hartmann, recorded his experiences in a personal diary later recovered after the war. His entries reveal a steady decline in morale. In mid-1943, he still believed adjustments to German procedures might restore the balance, but by late summer he admitted that British countermeasures were evolving faster than German responses. By the end of that year, he acknowledged that German forces were falling behind not only in quantity of equipment but also in technical sophistication. Early in 1944, he concluded that victory in the radar conflict was no longer realistic, writing that German crews were essentially operating without reliable sight against an opponent who seemed to anticipate every move. German air defenses finally unraveled in 1944 as Allied control of the skies became overwhelming. During the June landings in France, the Allies launched one of the war's most elaborate electronic deception plans. Operations known as Glimmer and Taxable created false radar signatures suggesting enormous invasion fleets heading toward areas away from Normandy. Balloons carrying reflectors, aircraft dispersing metallic strips, and carefully timed patterns of signals combined to simulate phantom armadas. German radar stations, already weakened by sustained jamming, could not reliably separate real threats from fabricated ones. As a result, commanders hesitated and misdirected resources, contributing to the success of the landings. By the final phase of the conflict, American heavy bombers commonly carried multiple jamming systems. One of the most widely deployed devices, often referred to as the carpet jammer, was produced in numbers exceeding 14,000 units, more than all other Allied electronic warfare systems combined. This scale reflected both industrial capacity and the strategic priority placed on disrupting German radar. British bombers used comparable equipment and specialized RAF units, most notably No. 100 Group flew aircraft dedicated to electronic warfare. These escorts created zones of interference around bomber formations, significantly lowering loss rates during raids. The implications of these developments extended well beyond immediate battlefield outcomes. Before 1940, electronic warfare had barely been recognized as a distinct field. By war's end, it had become central to modern military operations. The interplay between radar detection, countermeasures, and countermeasures established a pattern that would shape technological competition for decades. The rapid cycle of innovation demonstrated that any advantage in this domain was temporary. Progress depended on constant adaptation in a contest between seeing and concealing. Interrogations conducted after Germany's surrender clarified how decisive this technological contest had been. Radar specialist Dr. Hans Pendel told Allied intelligence officers in mid-1945 that the introduction of metallic window strips in 1943 marked a turning point from which German defenses never fully recovered. From that moment onward, German engineers were largely reacting to Allied advances rather than setting their own pace. By 1944, he estimated German systems lagged several months behind Allied countermeasure technology, and by the following year the gap had grown even wider. He argued that the outcome did not stem from inferior scientific ability, but from the Allies' greater production capacity and more effective intelligence. Senior commanders shared similar conclusions. General Joseph Kammhuber, who had overseen Germany's integrated night fighter and radar defense network, acknowledged that the system, which had worked well earlier in the war, became outdated almost overnight once Allied countermeasures were introduced. What had once been a formidable defensive structure quickly lost reliability in the face of sustained jamming and deception. In retrospect, many German officials saw the electronic dimension of the conflict as a race they were structurally unable to win. Efforts were made to modify and improve German radar systems, yet each adjustment was quickly neutralized by Allied countermeasures. Within weeks of every technical change, British jamming methods adapted in response. The situation reached a critical point when German night fighters themselves became targets. Allied aircraft began using devices that locked onto German radar emissions. By turning on their own equipment to search for bombers, German crews effectively revealed their position. Aircraft that were meant to hunt now acted like signals guiding enemy fighters toward them. The mental strain on night fighter crews was severe. Activating radar once their primary advantage now carried the risk of immediate detection by British fighters equipped with receivers designed to locate those transmissions. What had begun as a technological edge transformed into a dangerous liability. The air campaign against Germany ultimately succeeded not only because of the volume of bombs dropped, but because electronic warfare disrupted and confused German defensive systems. Post-war research confirmed the impact of these developments. Before widespread deployment of electronic countermeasures such as aluminum window strips and airborne jammers, bomber losses were high. In 1943, average losses for British bomber missions were around 4.5% per sortie. By the end of 1944, once comprehensive jamming support was standard, losses had dropped to roughly 1.5%, even though German defenses had grown stronger numerically. The US 8th Air Force experienced comparable results. Once carpet jamming became routine, losses to anti-aircraft fire decreased dramatically by about 3/4. The number of aircrew who survived because of these technologies was substantial. Conservative estimates suggest that radar countermeasures alone prevented the destruction of hundreds of heavy bombers in the American 8th Air Force, sparing thousands of crew members. British Bomber Command reported similar outcomes, with several hundred aircraft reserved due to reduced loss rates linked directly to jamming and window deployments. Behind these figures were individuals, pilots, navigators, gunners who returned home at war's end because Allied scientists had found ways to outmaneuver German radar. The conflict in the electromagnetic spectrum proved as decisive as combat fought with bombs or bullets. One German radar operator, Klaus Hartmann, witnessed the first large-scale use of window. He survived the war and later emigrated to the United States, eventually working as an electronics engineer in California. In an interview decades later, he recalled the night when his radar display suddenly filled with confusing echoes. Though he did not fully understand what was happening, he immediately sensed that something fundamental had changed. The British, he realized in hindsight, had achieved what German planners considered impossible. They had rendered bombers effectively untraceable by overwhelming radar systems with false signals. Looking back, Hartmann believed that moment marked a turning point in the air war. Germany's technological advantage in radar evaporated almost overnight. The episode stands as one of the most striking examples of a rapid technological reversal in military history. It illustrated that success in modern warfare depends not only on weapons and manpower, but also on innovation and the ability to solve problems faster than an opponent. German radar crews remained skilled and committed. Yet they faced a contest they could not win once Allied engineers introduced effective countermeasures. The implications extended far beyond radar itself. Electronic warfare demonstrated that modern conflicts unfold simultaneously across multiple domains. Dominance of the electromagnetic spectrum became as essential as control of territory, sea lanes, or airspace. Countries that understood this and invested accordingly gained decisive advantages. Despite Germany's technological capabilities in 1943, it never fully recovered from the shock delivered in late July when simple strips of aluminum foil disrupted complex radar networks. The struggle in the invisible realm had already been decided before many commanders recognized that a new type of warfare had begun. Few defeats are more damaging than losing a contest without realizing it was underway until the outcome was already sealed.